Today we'll be going over largest divisible subset. So this question is basically asking you to find the largest group of numbers in the provided input such that every number can meet this condition. So the larger number mod the smallest number is equal to 0. So that means when you divide by the smaller number, the remainder is 0. And it looks like if there are multiple solutions, any subset is fine. Add an example to help us build some intuition around how to solve this question. So say we have 4, 8, 10, 16, 20, and 240. So let's look at these two numbers first. So 8 can divide 4 evenly, right? And that means that the subgroup that I have has two elements, 4 and 8. 10 cannot divide 8, so 10 cannot be a part of this subgroup. 16, however, can divide 8, which means that 16 must also be able to divide by 4 evenly. So it must be a part of this subgroup, and that gives us a subgroup of size 3. So this should lead to a dynamic programming solution because we know we can kind of break the problem down into smaller pieces and reuse previous computations. We're going to initialize our DP array to all ones, and essentially what this is saying is at this index, what is the largest subset that I've seen so far? And they're all going to have size 1 initially. So now let's process the rest of the array with two for loops. And the way this is going to work is we're going to fix our I and iterate through the rest of the elements using j. And what this means is basically, does the element at j divide the element at I evenly? If so, we will add 1 to the size of the subset that we see at element I. Let's take a look at 4 and 8. So 8 divides 4 evenly, which is why now the size of this subset is 2. 10 does not divide 4. 16 does divide 4, so that's why this is also updated to 2. 20 divides 4, 240 also divides 4. So each of these subsets are going to have size 2 now, because it could be 16, 4, 24, or 244. The next iteration, and I is now at element 8. So does 10 divide 8? No, it doesn't, which is why the maximum subset size is still 1 here. 16 does divide 8, and now it has a size of 3. So 16, 8, and 4. So notice the way we updated this is we just add 1 to the maximum subset size at this position, or what we saw at element 8. Does 20 divide 8? Nope, so we just preserve the previous DP value. And does 240 divide 8? Yes, it does, and we add 1 to what we saw 8, and that gives us 3. So these subsets with size 3 right now are 16, 8, 4, and 240, 8, and 4. Move on to our next iteration. I is at value 10, and does 16 divide 10? No, it doesn't, which is why this value is unchanged. Does 20 divide 10? It does, so we will add 1 to dp of I, which is 1, and that gives us a value of 2. Now, 240 divided by 10, that also gives us a remainder of 0, so we'll add 1 to dp of I here. However, notice that 3 is more than 1 plus this value here. So this implies that our dp equation is actually going to be what it was currently, or 1 plus dp of I. Whichever one is higher, that's the value that we'll take. That's why we keep this at 3 as opposed to updating it to 2. So for the next iteration, let's say I is at 16 now. 20 doesn't divide 16, but 240 does. So 240 plus dp of this value, which is 3, gives us 4. And we see that the maximum size is 4. And we can trace this back by looking at, okay, it was 4 at 240. Now, if we move to the left, we want to find a subset of size 3 because we're not including this 240. So that would be 16, and then 2 would be 8, and then 1 is 4. And that's how we compose our final subset. So now let's look at the code. First we'll handle an edge case. If no numbers are provided, we'll just return an empty list. Then we need to sort the numbers, And the reason for doing so is that we need to make this I and j double for loop traversal work. And if it's not sorted, well, this line is not going to ever be true, right? So we will always want to be checking the larger number divided by the smaller number has a remainder of 0. And this line is the key equation for the update of the DP array. We either want to take the maximum of what we have so far, or we want to add 1 to dp of I. What we want to do is, after we have the maximum size of that array, we want to be able to reconstruct the array to figure out what elements were inside of it. So we find what the best value was, we find out which index it occurred at, and then we find the corresponding value in the original number array. We know that that has to be part of our output, so we'll just put it in here. And say the best size we had was 4. Well, now the best size that we're going to be looking for is 3, right? So we subtract off 1, and then we iterate backwards from the array, which means that we're processing elements in descending order. So if the DP value is equal to our current best, and the best value mod the number that we're looking at is equal to 0, which means that it's part of the largest subset, then we append the number that we're currently processing. And because, okay, now we have another element in the maximum subset, we are looking for 1 less than the best size that we found. And we do this all the way back, and we would return output.